Hi, everybody. Welcome. Sorry we're late. We've had technical issues. This is EarthSky's Sun News of the Week. I'm Deborah Byrd, and we are here with Dr. C. Alex Young, who's a heliophysicist at NASA Goddard Space Flight Center in Greenbelt, Maryland. So Alex is having some connection issues. Alex, you're still here, right?
I'm still here. Can you hear me?
Absolutely. We can hear you. Awesome. Okay. So,
Okay.
Alex is also the co-author of our daily Sun News post at earthsky.org. And Alex, what is this big, beautiful blue image we're seeing here on the screen? What is that?
Well, this is an image a video that I made of the sun over a week. This is observed by the SDO, or Solar Dynamics Observatory. And what you're seeing is the visible sun, which is showing us the sunspots. That's the whitish part with the black specks. And then the sort of wispy teal stuff you see over top of that is actually ultraviolet images. And when you see them very bright, they're actually showing you solar flares.
Oh, that's so cool. So what we're seeing here is a really active sun. Right?
Yeah, so it's an exciting, this is an exciting time because right now we're close to, or maybe even in, what we call solar maximum of the peak of the 11-year solar cycle. And right now there's all kinds of stuff going on all the time. And in fact, something we were going to talk about is the August data just came out for the monthly average of the sunspot number, and it is the largest in the cycle, and it's the largest it's been in 23 years.
Wow. So how large is it? Like, what does that mean? What's the sunspot number, first of all?
Well, the sunspot number is it's actually not the number of sunspots. It's something we calculate. So what we do is we actually do count the number of sunspots, but we also add a factor of all the groups of sunspots. So, and that together gives us a number called the sunspot number. We've been using this for centuries to estimate what's the number of sunspots and what are the groups of sunspots we see, to give us an indication of how active the sun is. And so right now we've hit a number in August. It's the monthly average. We take all those daily numbers and we add them up and divide by the number of days. So it was 215 for August, and that is the highest it's been since September 2001, which was 2 solar cycles ago.
Wow. And so we are maybe at the peak of the sunspot cycle.
Maybe, but we're excited. We thought that July was the maximum, and it turned out then that August became the maximum. So the big question is, what's this next month going to be like?
Ooh, yeah. Will September go even higher? So that's exciting, because wasn't the last sunspot cycle sort of a low cycle? A weak cycle? Cycle 24?
Yeah, the last sunspot cycle was in fact the lowest in 100 years.
Whoa. But this one's been higher.
Right. Well, this one has been higher, but that's actually a surprise, because scientists at NOAA and NASA, who make a prediction the beginning of every sunspot cycle, which is the minimum, and the last minimum was in 2019, and they made a prediction that this cycle, which we number 25, was going to be the same size as approximately the previous cycle. And it's turned out that they were completely wrong. It's been so much bigger than we expected.
It has been so exciting. This has been, we at EarthSky, we track the sun every day. We have a post about the sun that changes every day. And, it has just been so exciting over this past year to see what's going on in the sun. So sunspots, solar flares, what else, Alex? X flares.
X flares, yeah. So we measure the size of solar flares by the amount of X-rays that are put out, and we have a scale, kind of like the Richter scale, which is actually goes in powers of 10. So 1, 10, 100, and so on. And X is the largest on that scale, and we've had more X flares in up right now just to the approximately middle of the cycle than we've had in the entire previous cycle.
Wow, that's so cool. And we now have this capability. Like, I'm curious about this because you mentioned that sunspot number has been measured for centuries, but now we have spacecraft that, and we have different ways. We don't have a spacecraft that can see the backside of the sun, do we? A sun observing spacecraft, but we do have like the spacecraft on Mars that can look toward the sun.
We don't.
Right. So we
Right.
just have spacecraft that can see one side.
Right. But, actually, that's kind of right. However, we don't see the backside directly, but we use a technique that's very similar to seismology, which is used here on Earth to measure sound inside the Earth, which allows us to measure earthquakes. And it also allows us to actually indirectly image what the inside of the Earth looks like. And we do the same thing on the sun. The Solar Dynamics Observatory, SDO, takes sound waves from inside the sun. They're converted into light, and that then allows us to work backwards and figure out what's on the other side. And we can see sunspots on the other side.
That is so cool. And so we know as the sun is rotating, as you see it rotating here, that every so often there's a big sunspot that'll be just coming around the corner, and you guys will know that it's on its way, partly because of helioseismology, that sound wave technique, and partly because you can see things blown off the edge. And let's have the next slide and talk about that slide, because this was an event that happened earlier this week. Oh, well, this is just showing. Tell us, before we move to that next slide, tell us about this. This is the
so this is the solar cycle, showing you from solar cycle 23 up to now, solar cycle 25. And so you can see here that the largest value in 23 years was the September 2001, where it was 238. And so the value that we saw last month was 215. And that last cycle, or so when I say the solar cycle 23, was actually a very active cycle. In fact, we had some of the most historically and some of the largest solar events that we've ever seen. We had what was called the Halloween storms in October, November of 2003. And those happened, you see 2003 is actually on the way down. So one of the interesting points that's showing you there actually is a lot of times the really interesting stuff happens after the peak. And so that's one of the things we'll be looking forward to, but we'll also be looking to see, is this solar cycle going to end up being bigger than 23? And that's still up for, it's up for grabs.
Yeah, that's cool. And it almost looks like there's a little bit of a double peak going on there around 2000.
You're very observant. Yeah, you're extremely observant, because that's really true. There is a double peak. Yeah. And not every solar cycle has the double peak, but many of them do. We believe this current cycle may have a double peak. And what that actually means is it means that the northern and southern hemisphere are not in sync. Each peak corresponds to a different hemisphere. Huh. So right now, I believe the southern hemisphere was more active than the northern hemisphere. And so right now we're expecting more from the northern hemisphere, and that will more than likely give us this double peak.
Cool. Let's move to the next slide, because there's too much to talk about here. So this is an image that we got earlier this week, and this is the one that produced the chunk of sun stuff, called a coronal mass ejection, or a CME, that went toward Venus. Can you tell us about that, Alex?
Yeah, so this was an event that we saw these big loops, but in fact, the sunspot area that came from is just around the corner, or we would say over the limb of the sun. So it's that what that means is we're not seeing the full event because in fact, what's happening is not only happening where the sunspot is, but it actually happens higher up in the atmosphere, the part called the corona. And so the flare that we saw, the very brightening in X-ray, was a large M flare. So M is right before X. But because we didn't see the whole flare, it probably was a lot bigger than what we measured. And the other thing is you see those big loops at the end. Those are a special kind of loop that doesn't come from every flare. This is a type of flare called a two-ribbon flare or an eruptive flare. And we call those loops post-flare loops. They came after the full flare. And what that's telling us is you typically see that when you have a large eruption of stuff, as you mentioned, the coronal mass ejection. And so that's indicating that there probably was a very large coronal mass ejection. And sure enough, that's what we saw with the SOHO coronagraphs, which are creating these artificial eclipses. And that's what NOAA and NASA have modeled happened.
But it wasn't coming toward us.
Right, exactly. So it happened over the limb. The flare we could see, but the stuff went out in a sideways direction. Now, sometimes when you have a coronal mass ejection that goes sideways, they create big shock waves. And so maybe you would feel that shock wave even here at Earth. So they still check for that. They found out that that's not what was going to happen. However, they did some more modeling, and sure enough, this thing is heading straight for Venus. And that's a really exciting thing. Unfortunately, we don't have any current data from Venus like we do from Mars, but Venus doesn't have a magnetic field like the Earth does. And so how this coronal mass ejection interacts with Venus should be very different than what happens here on Earth.
And so when you say we don't have any data from Venus, that's because we don't have any spacecraft there, right?
Correct. We don't have any spacecraft. We're planning to send another spacecraft to Venus, but that's actually going to be going down into the atmosphere and not orbiting the planet, which is kind of what we would want.
And so what's expected to happen? So it's going to be different at Venus than it would be at Earth. What's going to happen?
Well, so because Venus does not have a magnetic field, it doesn't have what we call a magnetosphere. So a magnetosphere is a big magnetic shield around the Earth that's created by the Earth's magnetic field interacting with all this sun stuff. So that kind of acts as a shield, but that also sometimes when these events are large enough, that shield gets rattled, kind of like ringing a bell. And when that happens, it creates what's called a magnetic storm or a geomagnetic storm here on Earth. And that can have all kinds of crazy effects. We get the beautiful aurora, but you also get things like power grid outages, communication outages, and things like that. So Venus doesn't have that. So Venus, because it only has this atmosphere, the atmosphere itself is creating a special type of layer called an ionosphere. So we have those here, but they don't have Venus does not have a magnetosphere. So Venus would not experience these geomagnetic or Venus magnetic storms. And the properties also mean that the atmosphere of Venus can even be blown away, which is something that happened to Mars billions of years ago. So it's it's very different. Yeah.
Yeah. Wow. So it's like, so this stuff leaves the sun and Venus does not have a magnetosphere, a magnetic shield. And so part of the atmosphere can get stripped away.
Right. We've seen that happen. In fact, that actually happened in those famous 2003 storms at Mars.
Wow.
So understanding what's happening at Venus is actually important important for us to understand Mars. Someday we're hoping to go back to Mars, but in order to do that, we really need to understand how all this solar weather or space weather impacts Mars. And Venus is another opportunity to look at a planet that has some similarities to allow us to understand that.
And so this is probably going off the subject, but if you were on Mars and one of these big solar storms happened, and because Mars doesn't have a magnetic field either, but a solar storm happened, would you have to go underground or if you were an astronaut, would you have to get into some shielded area to survive that?
Yes, you might have to. Now, one of the things is there's actually a different kind of aurora that happens at Mars. So Mars does in fact have aurora, but it's different than the aurora we have here. But one of the things that can happen with these large coronal mass ejections is they can push more solar stuff in front of them that creates this big spray of very, very high energy particles, which really is high energy radiation. So that is something that then can impact Mars, and that would be detrimental, dangerous for astronauts. So they would potentially have to go under some kind of shelter or go underground. And these are one of the things that we have to think about before we can actually go to Mars.
You got to be brave to be an astronaut.
You really do. I mean,
Wow.
Well, one of the things is astronauts are very aware that when you go up into space, even at a low orbit like the ISS, you're going to be exposed to higher amounts of radiation over your lifetime. That's a danger that they have all committed to do. And when we go to the moon and eventually to Mars, that radiation could be even stronger. So it's something that they're aware of, and that is a commitment that they make to be an astronaut, which is pretty impressive.
That's right. Like I was just reading 2012 by Kim Stanley Robinson. I just finished it a little while ago. And one of the things, and it's all about people living out in the solar system. And one of the things they talked about in that book was how people had a lifetime radiation number. And you didn't want that lifetime radiation number to go up from all these various events that you as a spacefaring person would be exposed to radiation different ways at different times. You didn't want that lifetime number to go up over a certain amount, or you would be in trouble. You would die.
Exactly.
So, yeah. Okay, let's move
so
on.
All astronauts have to wear these little radiation detectors just to measure that. So yeah, but let's move on.
Wow. Okay. Yeah. Natalia, just show the next 3 slides. We're just going to show a few slides of beautiful prominences coming up off the edge of the sun. And Alex, can you tell us what the difference is between a filament and a prominence?
Yeah. So what you're looking at here, you're seeing things that are shooting off the sun and things that are sitting in the background, above the edge of the sun. Those are called prominences. And then there also, if you look in this particular image, you can actually see these little dark structures, kind of dark lines on the surface, on the disk of the sun. And those are filaments. But it turns out they're the same thing. We didn't know that many, many years ago, but it's all a matter of perspective. So when you look at these structures on the disk, they are much cooler and therefore darker than the background of the sun. So they appear dark. But when you look at them on the edge in space is much cooler, and those filaments are actually much brighter. So we call them prominences.
Cool.
So they're exactly the same thing. It just depends on how you look at them.
So little sun vocabulary lesson today. Filaments are the ones that are on the sun, and prominences are the ones that shoot off the sun. So we're going to be using those words a lot, and we do use those words a lot in our daily sun news post at earthsky.org. But let's look at the next slide. Okay, so to me, this looks like kind of an alien sun temple. but it's not. It was this image was the astronomy picture of the day from earlier this week. What is this, Alex?
That's an amazing, that is actually a prominence. But what we're looking at is a different type of light. So this is, this I'm guessing was probably an amateur astronomer or an astronomer that has a special type of telescope called an H alpha telescope, or a telescope with an H alpha filter. And that's a very narrow wavelength of light that happens to be basically red. And when you look at the sun in that narrow wavelength of light, you're seeing a different parts of the sun. So the prominences give off light in several different wavelengths of light. So they look different depending on which wavelength you're looking at. And this is really cool because you see all those fibrily like structures. It kind of looks like a carpet on the surface. That is, in fact, something we call spicules. They are little fibers of solar material that are shooting out. And we can see those when we look in H alpha. This is a really exciting wavelength. I used to work for a telescope on the Hinode spacecraft called the Solar Optical Telescope, and we looked in H alpha. And it's really, really cool. And this is something that's neat because you know, as an amateur astronomer, you can get H alpha filters that you can look at the sun with, or, you know, even H alpha telescope. So this is just a gorgeous image, and I've always excited to look in H alpha pictures.
It's very cool. So it was Andrea Vanoni in Italy who took this image and gave us permission to use it here. So thank you, Andrea. You can find him on Instagram at Astrovano on Instagram, and we really appreciate it. So Alex, thank you. That's our Sun News of the Week. And this is the second time we've done this. We're going to get smoother at it as the weeks go on.
Hopefully next time I'll be a real person and not just a voice in the background.
Yeah, we'll try to make Alex more than a disembodied voice next time. You've been watching EarthSky, Sun News of the Week, and come on over to our website, earthsky.org, for daily sun news and to read about the far side X flare that was just confirmed a few hours ago. We will be back live at 17:15 UTC, which is 12:15 p.m. Central on Monday, September 9th. Our guest will be veteran moongazer and author Robert Reeves, and he is going to clue you in on all the different ways that you can love the moon. From Alex and me, thank you. See you then.